Now going to the number of the nature of orbitals involved, we have got this classification once again. We have talked about this thing already. What are going to be the cases for the carbocations or free radicals? What are going to be the cases for the alkenes and alkyl benzenes? So basically, sigma bonding electrons going into pi star or sigma star are going to be the cases of the carbocations, alkenes, and your methyl chloroform or alkyl halide, those situation. And then when sigma bonded electrons were going into the pi star molecular orbital, that is what we have just seen was the case of the benzyl halide or the alkyl halide. Also, we can see the non-bonding electrons also can be going into the pi star. Methyl glycosides are one of the examples. We'll be seeing that in the cases of anomeric effects in detail later. Just to have an idea how these kind of examples are there. So we have got the first example where we have got the carbon sigma to p bond, like sigma p conjugation when the sigma p hyperconjugation when that's taking place. We have got the examples of carbocations and radicals. When we have got sigma to pi star, we have got alkenes and alkyl benzenes, and when you get sigma to sigma star, this is going to be case of the methyl chloroform or the alkyl halide, 7 alkanes as well. We'll see the examples of these. So that is these two first cases onto the left. This is for carbocation and that is for the radical. This is sigma to p conjugation, basically hyperconjugation basically, and this is the case of alkenes. And what we have shown here is this antibonding molecular orbital. So this is going to be the case of alkene where we are going to have the sigma to pi star hyperconjugation. We are seeing this on the basis of just the orbitals involved when this kind of electrons delocalization is taking place. And I hope you might have noted already when this is a single electron present in this orbital in the case of radical, then the direction of this arrow we are keeping is different than what we are otherwise using in the case of normal delocalizations. And this is the case when the electrons of the sigma bonded electrons are going into the sigma star antibonding molecular orbital. That kind of situation is also going to be there in the case of hyperconjugations. Next example is going to be where sigma electrons are going into the empty molecular orbital. So just one case we are having here, that is benzyl chloride or situations like that. We have just shown here one chlorine. We can have even more chlorine. Similar situation will be arising there as well. So what was happening here? This is filled pi molecular orbital, like occupied molecular orbital. This is there, filled pi molecular orbital, and here we have got empty sigma star. So electrons are going from the pi orbital into sigma star orbital. That is the case of the benzyl halide, and that is basically one of the case of the reverse or negative hyperconjugation as well, what we have just seen. We also have the orbitals which can be involving from non-bonding electron to the empty orbital as well. Two examples we are going to take here. One is going to be the case of the ethers, we can say. Another one is going to be the case of the what we understand as the we can call as acetal, or derivatives of the acetals can be understood as the glycosides. So here is the first example. This is the like alcohols or ethers we can understand basically. We have got Z heteroatom which is having a lone pair. It can be either of the ethers or it can be amines. Amines we can understand, maybe any other example we can think. We need to just replace this one of the valence, whatever this structure we have drawn. One of these bonds we can replace with the lone pair, then it can be the case of ethers, and right now this can be the case of amines as well. So what was happening? This non-bonding electron which is present on this heteroatom Z, this is going into this anti-bonding carbon hydrogen molecular orbital. And please note, when we are saying the electron acceptor ability, carbon hydrogen bond has very small electron acceptor abilities. This kind of delocalization will not be as much effective as it would be when the sigma star orbital is going to be quite electron demanding, something like carbon chlorine bond, something like carbon fluorine or carbon oxygen bond. Those are going to be quite electron demanding. This kind of hyperconjugation can be very much effective in those cases. Here, although it happens, but the extent of delocalization is going to be quite smaller. The stabilization what can be coming, it will be significant but not that much as it can be in case of highly electron demanding or the orbital which is having very high electron acceptability. Depending upon that, the extent of hyperconjugation can be changing, right? Another example we have taken, this is the case of, say, if you put here basically oxygen, if you put here oxygen atom, then this is going to be the case of glycosides, that is, we can say acetals in fact. So there, if you have got oxygen this time here, like this is going to be a carbon oxygen bond, this carbon oxygen bond will be quite electron demanding. This kind of delocalization can be quite dominant, and this will be bringing in quite higher stabilization in comparison to this kind of situation. This is going to be quite electron demanding. If this is more electron demanding, that means there will be better electron condensing ability. This is electron demanding, but this is relatively less electron demanding. That sigma star orbitals what we are talking about. You might have already noted how we have shown the sigma star molecular orbital for the carbon hydrogen bond and how we have shown it for the carbon oxygen bond. You have understood the molecular orbital diagrams, how the different orbitals when they are interacting, which kind of the molecular orbitals will be formed.